Acceleration is the change in velocity over a period of time. Uniform acceleration means that in every period of time, the velocity changes by the same amount. On a VT graph, we can see this with a straight line. So here, if I go across 1 second, I go up that much, the velocity changes by a bit. If I go across another second, the velocity changes by loads. There's a different, for 1 second across, it's a completely different change in the velocity. Whereas on the straight line section, I go across 1 second, that's how much my velocity changes. I go across 1 second, that's how much my velocity changes. I go across 1 second, that's how much my velocity changes. So the change in the velocity, which is the acceleration, is constant. So what we're looking for on a VT graph is a straight line. So the equations we're going to look at, the equations of uniformly accelerated motion, they describe a period of time during which the change in velocity every second is always the same. And that on a VT graph looks like a straight line section. So these equations are only true for a section of time on which the acceleration remains constant. The VT graph has a straight line. We're going to use this rather boring story speed time velocity graph to come up with two equations of uniformly accelerated motion. Note that on this section of the graph, the graph is straight, so the acceleration is uniform. Okay, first equation comes from the fact that the gradient, as we've said many times, of this graph is acceleration. The gradient is the change in velocity divided by the change in time. The change in velocity here is v minus u, and the change in time is t. So the gradient, which is the acceleration, is v minus u over t. And if we rearrange that, we get v equals u plus at, which is the first equation of uniformly accelerated motion. The second equation comes from the fact that the area under the VT graph, or between the VT graph and the time axis, represents the displacement of the particle, and we use the letter S for displacement. So the area under here is a trapezium, and the area of a trapezium is given by the sum of the parallel sides. So that's this side and this side. One of them is length u, one of them is length v. So the sum of the parallel sides, u plus v, times half the distance between them. So that's multiplied by half of t. And that gives us the displacement. And that's the second of our equations of uniformly accelerated motion. Actually, there are only two. The other three I'm going to get from these two. So the first thing to notice is that equation 1 has got a u, a v, an a, and a t. There's no s in it. Out of our Suvat quantities, we've got s, we've got v, we've got a, we've got t, but there's no s in it. And the second equation, this has got an s and a t and a u and a v, but no a in it. And what we'd like is an equation without u, an equation without v, and an equation without t. And then if that quantity isn't used in our problem, we can pick the equation that doesn't have that quantity in, and it's going to make our life easier. So the way we're going to do that is with simultaneous equations. To get an equation without v in, I'm going to take the v from this equation and sub this u plus at into this equation wherever it says v. To get an equation without u in, I'm going to rearrange this first equation to say u equals, and then I'm going to stick it in to the second equation wherever it says u, and I'll have an equation without u's in. And finally, to get an equation without t, I'm going to rearrange it to say the first one to say t equals, and then I'm going to stick it into the second one in there, and then I'll have an equation without any t's in. Okay, so starting with v equals u plus at, and sticking u plus at into v in the second equation gives us s equals a half t u plus at, s equals a half t 2u plus at, S equals, expanding the brackets, ut plus a half at squared. And that's our third equation there. Next, we're going to rearrange this first one to say u equals. So u, let's write it the other way, v minus at equals u. And that's going to go in here, in the second equation. S equals a half t, v minus at plus v. S equals a half t, 2v minus at. Expanding the brackets, S equals Vt minus a half At squared. And that is our fourth equation. And finally, we are going to rearrange the first equation to say T equals, this is a little bit harder, and stick that into the second equation here where it says T. So we have V minus U is AT, so divided by A is T. Then we're going to stick that into the second equation. S equals a half T U plus V. I'm going to multiply both sides by 2, giving 2S equals V minus U over A times, I'm going to write V plus U actually instead of U plus V. Multiply both sides by A, giving V minus U, V plus U is 2AS. And then expand the right hand side and you'll get difference of two squares. V squared minus U squared, and that gives us our final equation. V squared is U squared plus 2AS. That's the fifth equation. That's got no T in it. So in summary, we are looking at a section of motion which on a velocity time graph would have a straight line. Any section with a straight line. That means that for every second we go across, we go up or down by exactly the same amount. Using the fact that the gradient of this graph is equal to acceleration, we get the equation v equals u plus at. Using the fact that the area under the graph, the area between the graph and the time axis, is displacement, we get s equals a half t u plus v. By rearranging don't need to rearrange, by rearranging the first equation to say v equals and sticking it into the second equation, we get the third equation, s equals ut plus a half at squared. By rearranging the first equation to say u equals and sticking it into the second equation, we get the fourth equation, s equals vt minus a half at squared. And by rearranging the first equation to say t equals and sticking it into the second equation, we get the fifth equation, which is v squared equals u squared plus 2as. Notice that the first equation has, out of s, u, v, a, and t, it doesn't have a, what doesn't it have? It's got a v, it's got a u, it's got an a, and it's got a t, but there's no s. The second equation has got an s, it's got a t, it's got a u, and it's got a v, but there's no a. The third equation has got an s, it's got a u, it's got a t, it's got an a, but there's no v. The third equation has got an s, it's got a v, it's got a t, it's got an a, but there's no u. And the final equation has got a v, it's got a u, it's got an a, it's got an s, but there's no t. And that's how we're going to choose which equation that we want. The quantity that is not in the problem, not interested, don't care.